During severe dehydration, the mammalian kidney must preserve systemic plasma volume to maintain blood pressure. It accomplishes this by extracting water from the developing urine, leaving behind a highly concentrated waste product. But this extraction faces a strict anatomical constraint. The human body does not possess active transport pumps capable of moving water molecules directly. Because water cannot be physically pumped, it must be manipulated. The only way to move it is to create an osmotic gradient and allow the water to follow passively. The evolutionary answer to this problem is the countercurrent mechanism, a structural architecture within the kidney designed specifically to manufacture that required osmotic gradient. Concentrating urine is an exercise in solute engineering. This engineering relies on the juxtamedullary nephrons. These specialized filtration units extend their long tubular structures deep into the renal medulla. As fluid leaves the renal cortex and enters this downward path, it is isotonic to normal blood plasma, measuring roughly 300 milliosmoles per kilogram. This diagram illustrates the target destination. While the top of the nephron sits in a 300 milliosmol environment, the tissue at the very bottom, the renal papilla, reaches a hypertonicity of 1200 milliosmoles per kilogram. Building and maintaining an environment 4 times as concentrated as plasma requires 3 intersecting systems: the active multiplier in the loop of Henle, the passive exchanger in the surrounding capillary space, and the recycling of urea from the collecting duct. This vertical gradient is the engine. It provides the osmotic force necessary to pull water out of the filtrate right before it exits the body. The construction of this gradient begins in the loop of Henle. Fluid flows down into the medulla through the descending limb, makes a hairpin turn, and travels back up through the ascending limb. In the thick ascending limb, the NKCCC2 cotransporter uses secondary active transport to move sodium, potassium, and chloride ions out of the tubular fluid and into the interstitial tissue. Normally, water follows via osmosis, but this ascending segment is strictly impermeable to water. As solute is stripped and water locked inside, the rising tubular fluid dilutes toward 100 milliosmoles, while the outside interstitial space becomes hypertonic. The opposing descending limb is highly permeable to water through aquaporin channels, but impermeable to solute. Water passively exits the descending limb to equilibrate with the concentrated interstitial space. This pumping of ions and drawing of water is the single effect, which sustains a maximum concentration difference of 200 milliosmoles per kilogram across the tubule wall horizontally. A 200 milliosmol difference falls far short of the 1200 milliosmol target at the papilla. The system requires a mechanism to amplify this local effect. Amplification comes from the countercurrent multiplier. Pushing fluid continuously down the loop multiplies the local 200 milliosmol difference into a large longitudinal gradient. Visualizing the continuous flow of filtrate as discrete packets of fluid, the initial single effect establishes a 400 milliosmol concentration in the descending limb and 200 in the ascending. Next, a fresh packet of isotonic 300 milliosmol fluid enters the descending limb. This incoming fluid physically displaces the concentrated 400 milliosmol fluid, pushing it downward. As it moves, the ascending limb ion pumps re-engage, extracting more solute to maintain the 200 milliosmol horizontal difference. At this deeper level, absolute tissue concentration climbs to 500 milliosmoles. This continuous cycle pushes concentrated fluid deeper, with pumps extracting more ions at each step to stack the concentrations. Traveling down, water exits and fluid concentrates. Traveling up, ions are pumped out and fluid dilutes. This repetition culminates at the bottom of the loop, reaching 1200 milliosmoles per kilogram. The 200 milliosmol horizontal limit is never broken locally, but vertically, from the cortex to the papilla, the concentration multiplies 4-fold. The countercurrent multiplier uses continuous fluid displacement to stack the effects of localized ion pumps, creating a massive regional gradient at the renal papilla. But this gradient has a structural vulnerability. Tissues need blood, but standard capillary flow would reabsorb deposited solutes and wash away the concentration. The solution is the vasa recta, a specialized peritubular capillary network that physically parallels the U-shape of the loop of Henle. Blood flow through these vessels is exceptionally sluggish, moving under very low hydrostatic pressure. Unlike the loop of Henle, these capillaries are passively permeable to water and small solutes. As blood plunges into the medulla through the descending vessel, it absorbs solutes and loses water, equilibrating with the 1200 milliosmol environment. But as that blood rounds the curve and descends, the process reverses. It secretes those solutes back into the interstitium while pulling water back in, returning to a near-normal 320 milliosmols upon exit. Operating as a passive countercurrent exchanger, the vasa recta delivers necessary oxygen and removes reabsorbed water while keeping the essential solutes trapped in the medulla. Even with the vasa recta protecting the tissue, the physiological math has a gap. The active pumping of sodium and chloride only accounts for roughly 600 milliosmols of the final concentration. Urea provides the remaining 600 milliosmols of hypertonicity. Filtered urea travels through the nephron, but sections including the loop of Henle and the distal convoluted tubule are strictly impermeable to it. With water reabsorbed upstream and urea trapped inside, urea particles become highly concentrated within the tubular fluid as it descends. That trapped urea finally reaches the inner medullary collecting duct, the only segment permitting urea transport. During dehydration, antidiuretic hormone binds to V2 receptors on the membranes of these specific cells. This trigger inserts specialized urea transporters, UTA1 and UTA3, into the membrane. The concentrated urea floods into the medullary interstitium. The kidney manages urea as a functional osmotic tool, essential for reaching the final concentrating capacity of the medulla. The complete architecture of the renal concentrating mechanism operates as a single functional unit. The loop of Henle multiplies the gradient, the vasa recta protects it, and urea supercharges it. This brings us to the final path of the filtrate. A dilute fluid enters the collecting duct to make its final plunge through the renal medulla. In response to dehydration, ADH triggers the insertion of aquaporin II water channels into the collecting duct membrane. As fluid travels down the duct, the 1,200 milliosmol interstitium forcefully draws water across the now permeable membrane and out of the filtrate. This water is immediately absorbed by the vasa recta and returned to the bloodstream, defending systemic plasma volume. By removing the water, the kidney leaves behind a minimal volume of maximally concentrated urine. Human water conservation relies on this spatial engineering, divorcing active solute pumping from the passive movement of water to master the laws of osmosis.